Good morning. So this is going to be a quick little video on density and like temperature, just some outlying information that we need to get to. So let me share my screen here. Let's go. I got this. Oh, I don't like the way that paper looks. Okay. So we're going to call this, let's see, density. No, let's go backwards. Data. We're going to call this data, temp, conversions, and density. Okay. Cool. So when we talk about data, okay, there are two main types. We've got qualitative data, which is more descriptive. Just think about it, quality, right? This typically uses your senses. So you may talk about how something smells, its appearance, how it feels, even though we're not supposed to be touching things, etc. Right? We also have quantitative data. And this is going to be numerical in nature, right? Think the word quantity means numbers, right? So this would be like the mass, the volume, right? The size, anything that involves numbers. And, you know, you really can't get much simpler than that. Okay, so let's continue and let's change topics. This will be a real simple little lesson. Temperature conversions, all right? First of all, let's talk about temperature. When you measure the temperature, this is a measure of the average kinetic energy. Kinetic energy is the energy of motion. Oops, my words got mixed up in my brain. Average kinetic energy of, I'm going to write the particles of a substance, right? And what you need to realize is, like, even in a solid, it doesn't appear as though the particles are moving, but the particles are vibrating, right? Particles vibrate, even though we don't necessarily see it. Whether it's a solid, a liquid, or a gas, and that vibration creates kinetic energy, okay? The more vibration, the more energy. Kinetic energy, if you do not know, is the energy of motion, okay? So solids, liquids, and gases, they all have their particles here vibrating, all right? Now, the lowest possible temperature is referred to as absolute zero. Right? Absolute zero. And at absolute zero, what we see is there is no kinetic energy. Now, scientists haven't gotten anything to a perfect absolute zero, but they've gotten substances really, really close to absolute zero, like maybe 0.0 followed by numbers, but never 0.00000. Okay? Now let's talk about our temperature scales. And you're probably aware of these, right? You know that we've got the Celsius scale. We got the Fahrenheit. Let's see if I can spell it right. I think I spelled that right. And we've got the Kelvin scale. Okay? Now we will be most concerned with these two. And we will not be utilizing the Fahrenheit scale, you know, hardly at all. But we'll talk about it anyway. You guys are used to it because we use it in America, right? When we talk about the temperature, the weather, we use Fahrenheit. So, and let's look at how our temperature conversions will go. And my goodness, I'm memorizing. I hope my brain is working correctly, right? So let's say we have Celsius and we need kelvins, right? So that'd be a Celsius to Kelvin conversion. Well, that's actually extremely easy, because what we'll see is that the Kelvin temperature is equal to the degrees Celsius temperature plus 273. Simple as that. Now, we know that Celsius is degrees Celsius. We know that Fahrenheit is it degrees? I'm not sure. I'm not worried about it, to be honest with you. Kelvin is a big K, right? Right. And Kelvin does not go below 0. Right? You can never have a negative Kelvin temperature, right? And in fact, the lowest possible temperature, which we just said up here, is absolute 0, is equivalent to 0 kelvins. You can't get any colder than that, because at 0 kelvins, there is no kinetic energy. And if temperature measures kinetic energy, and at 0 kelvins, there is no kinetic energy, well, we can't get any colder than that. We can't stop moving any more than not moving, okay? So the lowest possible temperature is 0 kelvins. Kelvins does not go negative, and for that reason, we will always use a Kelvin's temperature when we're solving any math problems where you have to plug in a temperature. We'll see there will always be kelvins. We could do this backwards. Now, you can rearrange this, right? You could easily rearrange this equation to solve for Celsius, right? Degrees Celsius would equal our kelvins minus 273, right? So that would be how we would convert between Celsius and kelvins. We could also convert between Celsius and Fahrenheit, okay? Now, I go through my brain. I know that this boiling is 100 degrees Celsius. It's 212 degrees Fahrenheit. So I know that degrees Fahrenheit is equal to degrees Celsius times 1.8 plus 32. Okay? Let's make sure we're right. So if I put in 100 times 1.8 equals, and then I add 32, I do not get the right answer. Let's try that one more time. 100 times 1.8 equals plus 32. I do get the right answer. Okay, just wanted to make sure I gave you that equation correctly, and I did. Could we rearrange this equation so that it says degrees Celsius equals? Well, it looks like we would then take our Fahrenheit, divide it by 1.8, and subtract 32. Let's make sure that works. 212 divided by 1.8 equals, minus 32 equals, that does not look right. 212 minus 32 equal, 212 minus 32 equals, divided by 1.8 equals. Yes, so I've actually written that incorrectly, and it's going to go like this. It's going to be our Celsius, or Fahrenheit rather, minus 32 divided by 1.8. Okay. Yes, that works. I'm just making sure right now that I have not told you anything incorrect, and I haven't. Okay. I don't do these so often, so I have to make sure I remember. And this is how I remember, because I see that it gets bigger. So I know that in this equation, I need to do the operations that make it get bigger, the multiplying and the adding, and vice versa. Anyway, so let's go backwards. We were going to talk about data: qualitative, quantitative, observations, numerical, temp conversions. Okay, we did that. We talked about the temp scales, absolute zero, and how to convert between each. Let's now talk about density, okay? And we'll finish this up. Let's get a pretty blue color here. Let's look at density. Density is called a derived unit, right? We don't measure density directly, but it involves several different units, or two rather, right? We know that the density of a substance is equal to its mass divided by its volume. All right. Now, you need to be aware of some small things. Volume is temperature dependent. All right. You should know that as substances are heated, they tend to expand. And when cooled, right, they tend to condense, right? So since volume is temperature dependent, our density is also temp dependent. All right, not a big deal. Mass is not temperature dependent, right? It's always going to be constant for a given sample, no matter what temperature it's at. Actually, you could argue with me there, but we don't need to get into that. Okay, now let's look at some units for density. You might see grams per milliliter, particularly if it's a liquid, right? You might see grams per centimeter cubed, and that's typically used for solids, but not always, so don't get too hung up on that. And we use grams per liter if we're talking about a gas, because the gases take up so much more space. Remember that 1 milliliter is equivalent to 1 centimeter cubed, okay? So these can be used interchangeably. All right. Now we can density of irregularly shaped objects. All right. So let's say I have an object that kind of looks like this. I can't do the length. I can't, length times width times height is not going to give me the volume. So what I would do is I would get a graduated cylinder, right? And this is my graduated cylinder. And it's going to be empty. And then I would take that graduated cylinder and I would add some water to it. And students always say, well, Miss Murphy, how much water do I need to add? And I say, listen, honey, it really doesn't matter as long as you don't add too little and you don't add too much. So let's just put enough to make sure that when we put our object in there, it is submerged 100% and that the water does not go over the edge here. Okay, let's get rid of that little thing. Oops, let's undo that. We'll just, okay. Right, so then we're going to take that graduated cylinder with water in it. And let's say that right here, guys, let's make up a value. Let's say that we have 10.23 milliliters of H2O. All right, let's get that graduated cylinder back. That's not quite big enough. Let's get that graduated cylinder back. And let's rise the water. Let's make it higher. And it's going to be higher because we have now added the object, right? This being the object, okay? And we'll see that this object here is going to be down here in the water. And that's what caused the water level to rise, right? So our new volume, we'll just kind of make this up. Let's say it's 12.79 milliliters, okay? And what we are doing is we are getting the volume of the object by displacement, right? Just think of it, displacement. Well, displacement, what was displaced? The water. The difference in the volumes of the water will be equal to the volume of the object. So volume object is equal to 12.79 milliliters minus 10.23 milliliters. And that gives me a volume of 12.79. I could probably just do this easier right here. That's a 6, that's a 5, that's a 2. Sig figs are good. Okay, so that's the volume of my object. Let's assume that this object had a mass of 1.2 grams. Okay, well, the density of the object is equal to its mass, 1.2 grams, divided by its volume, 2.56 milliliters. 1.2 divided by 2.56, oops, 1.2 divided by 2.56 is going to give me, with two significant figures, 0.47, or 4.7 times 10 to the negative 1, it doesn't matter. And that's a gram per milliliter. Real simple, okay? That's how we would do an irregularly shaped object. Let's look at, oops, wrong word. Let's look at, what time is it? Okay. I gotta get to homeroom. Let's look at the density of a cube, all right? Well, you're gonna see Miss Murphy do some excellent drawing here. Let's just fix that one line right there. Okay, there you go. Well, in this case, we would do the mass, right, divided by the volume. But we would, in order to get the volume, we would do the length times the width times the height, all right? So we just make up some values there. Say that this is 2.0 centimeters. We'll say that this is 4.1 centimeters. And that, let's see, that would be that. Which one are we missing? I don't know. This here, maybe, whatever. Let's say that it's like 3.9 centimeters. And we'll make up a value for the mass of the object. Let's say that the mass, actually, let's change this one up. Let's say that we know that this object has a density of, so I'm just going to make this up, all right, 3.89 grams per milliliter. So what I'm about to do is form a practice question. Right, so this object has a density of 3.89 grams per milliliter. We are given its length, we are given its width, we are given its height. And the question is, what is the mass of this object, right? The object being the cube. Well, let's plug in our values. We know that D equals M over V. We know the density, right? The density is given to us right here, so I'm going to plug that in for that. It's 3.89 grams per milliliter is equal to the mass. Well, I don't know the mass. The mass is actually what I am looking for, right? So I won't plug anything in for that. And then I need the volume. Okay, well, I can easily get the volume by doing length. Oops, don't want to do that. Can easily get the volume by doing my length times width times height. Okay, so let's do that over here. And that would be this guy here, right? So let's get that. We would say 3.9 centimeters times 4.1 centimeters times 2.0 centimeters. All right, I'm going to do that. 3.9 times 4.1 times 2.0 gives me 31.98. And that's a centimeter times a centimeter times a centimeter, so it's centimeter cubed. Well, look over here. My density is given to me in milliliters, and my volume has a centimeters cubed. Well, recall that that is equivalent to milliliters. So I can use these interchangeably. And now I'm going to plug that in right here. Okay? And I'm going to see what I need to do to solve this problem. I'm going to multiply both sides by 31.98. Now, Miss Murphy is not here to teach you algebra. It is a prerequisite. 3.89 grams per milliliter times 31.98 milliliters. Guys, 2 sig figs, 2 sig figs, 2 sig figs, 2 sig figs. But I'm not going to round yet. This is my last sig fig. Equals. Now the milliliters cancel. And if I multiply this, 3.89 times 31.98 equals, I get 124.4. And my unit is a gram. This has 3 sig figs. This has 2 sig figs. This should be recorded as 120 grams. Okay? Okay. Let's do one more example. What is the volume of an object that has a density of 7.29 grams per centimeter cubed and a mass of, I don't know, 9.10 grams. Okay, real simple. So some of you guys are just going to run with this. Some of you guys are like, I hate math. Don't worry about it. What is the volume? Okay, volume equals question mark. Let's organize our stuff. It has a density of, okay, density equals 7.29 grams per centimeter cubed, and a mass of, all right, mass equals 9.1 of grams. I immediately, and hopefully you'll learn to do this, look at my units and make sure that they're the same. And they are. If not, I would have to make them the same. I know that D equals M over B. All right. Therefore, 7.29 grams per centimeter cubed is equal to M, 9.10 grams, over, I'm going to rewrite this so it doesn't confuse you. I'm going to write it a different way. I'm going to say 7.29 grams per centimeters cubed equals this many grams over my volume. Now, a lot of students mess this up because I think you mess up your algebra. Notice I need to multiply both sides by V, right? And then I need to divide both sides. Right now I have this. And then I need, hold on. And now I need to divide both sides by 7.29. And this is going to cancel. And I'm left with my volume equals 9.10 grams divided by 7.29 grams per centimeter cubed. 9.1 divided by 7.29. And I get a volume that is equal to 3 sig figs, 3 sig figs, 3 sig figs. That would be 1.25 grams cancel, centimeters cubed. That's about that. So, is there anything else I would want to tell you? No, I think that's good. Okay. Let's do one more thing. Let's say that I have a density of 5.0 grams per liter. And what would be my density in grams per centimeter cubed, right? So this is kind of a refresher from other things we've learned. Start with the number and the unit given, right? I'm going to continue with T-charts. We need to convert now, right? I'm going to go liters to milliliters to centimeters cubed, okay? I know I'm going to cancel my liters, so I'm going to put it there. I know that 1 liter is 1,000 milliliters. And now I'm going to go milliliters to centimeters cubed because every 1 milliliter is 1 centimeter cubed. So all I would need to do is divide that by 1,000, and I would get, 0.005 grams per centimeter cubed. Oops, Miss Murphy lost a sig fig, right? There's 2 here, so I should keep 2 here. You want to be careful with those things, okay? Or 5.0 times 10 to the negative third grams per centimeter cubed. Okay, figure out whatever questions you might have and bring those to me. And whoa, I'm gonna go. Okay, see you later.